There are all kinds of models that we can use for prediction. In this video, we'll learn about logistic regression, which is a type of model usually used for classification. If you've been paying attention, you might be asking, how can logistic regression be used for classification? Aren't regression models used for continuous response variables, rather than the categorical response variables that we predict with classification models? This is true. However, it turns out that we can extend the linear model to predict other types of data, such as categorical data. These extensions are referred to as generalized linear models. Essentially, we take the output of the normal linear model and we feed it into another function called a link function, which converts the continuous linear output into another type of data. Logistic regression is a type of generalized linear model where we can predict a binomial response variable. This is a categorical variable with two outcomes, such as 0 and 1, or true and false. So how do we convert linear output into a binomial response? We put it into a function called a sigmoid function. The graph here shows the underlying linear response in blue. The output of this, which I've called ylin on this slide, is then fed into the sigmoid function, and the output of this is shown in red. As you can see, the red line, the output of the sigmoid function, varies only between 0 and 1, even when the input linear function is greater or less than this. So how do we go from the continuous number between 0 and 1 coming out of the sigmoid function to a prediction of either 0 or 1 exactly? Well, we take the probability and we basically round up or down. If it's greater than 0.5, we round up to a prediction of 1. Otherwise, we round down to a prediction of 0. And that's logistic regression. We can create a logistic regression function in R using the GLM function as you see here. The GLM function is very similar to the LM function that we have used to create a normal linear regression. The first argument is the formula. This is the same as in the LM function and says how the binomial response variable, which I've called target, is related to the predictor variables, here called feature 1 and feature 2. An important difference, however, is that we need to specify what kind of link function to use in the generalized linear model. We want to predict a binomial variable, so we use a binomial function, which we specify using the family parameter. And it's pretty much that simple. Once we have the model, we can use it much like we would use the results of a normal linear model. For example, we can use the add predictions function just like we did with the linear model to create a predicted y value. However, we do need to add in the type equals response argument to make sure that the predicted values are the output of the sigmoid function, that number between 0 and 1 that you can see here in the pred column. To convert these into values of 0 and 1 exactly, we can then use a mutate function to add a new column, depending on whether the pred column is above or below 0.5, as we discussed earlier. As you can see here, we have stored these predictions in a column called outcome. There's actually a nice way to visually interpret the results of a logistic regression. Let's imagine that we have a binomial target variable that we want to predict, which here I've colored red and blue, and two predictor variables, feature 1 and feature 2, which I've plotted on the x and y axes of this graph. Well, we can fit our logistic regression, and we can see what the coefficients of the logistic regression are using the tidy function. These coefficients are analogous to slopes and intercepts in a linear regression. Using these, we can calculate something called the decision boundary, which is the point at which we decide whether a prediction is 0 or 1. And we can actually plot that decision boundary on our original graph. As you can see, it lies where you might expect it to, dividing the red and blue data fairly evenly down the middle. If we were to predict a point to the upper right of this boundary, we would predict a value of 1. If the point was to the left and below, we would predict 0. As you can see here, we would still misclassify some of our original training data, but the majority of the points would be correctly predicted.